bring it in for a landing here. We're going to get started. Thanks for coming. We're excited about what's going on tonight. This is a Theology on Tap. If you've not been before, this is something that Trinity Reformed Church in town puts together every so often. We try to have smart people like Bijan come and talk to us about interesting topics. So we're excited about tonight. I'm going to give an intro for Bijan, and it's kind of long. And I tried to cut out stuff, but this is a very accomplished man. So I'm just going to go for it. So Dr. Nemati is a principal research scientist at UAH. He's received his PhD in high energy physics from the University of Washington, based on his research on heavy quark decays. I'm sure we all know what that means. Detected at the Stanford Linear Accelerator Center. After postdoctoral work at the Cornell Synchrotron.
Yep.
Synchrotron. I know what that is. I just to see if everybody was there. He left particle physics to work on advanced astronomical instruments at the Jet Propulsion Laboratory. Inspired by work by other Discovery Institute fellows, particularly the Privileged Planet by Dr. Guillermo Gonzalez and Jay Richard, Dr. Nemati led several key test beds at JPL that together demonstrated the feasibility of astronomic detection of Earth-like exoplanets in the habitable zones of nearby sun-like stars. Dr. Nemati's work on the NASA's flagship space interferometry mission proved that the instrument could self-calibrate at the levels needed to detect exo-Earths. And for these achievements, Dr. Nemati was awarded NASA's Exceptional Engineering Achievement Medal. I've got a few of those, so it's cool to have you in those company. 2014, Dr. Nemati has been part of the development team of an exoplanet imaging instrument that will be part of NASA's Roman Space Telescope, scheduled to launch sometime after 2025. I'm going to stop there, but there's a lot more, and there's a lot that was cut out of that. So anyway, I think we've established your bona fides. It's exciting to be here, have this opportunity to hear you talk about this topic. So, welcome.
All right.
Please welcome Dr. Nemati.
Thank you all for coming tonight. I'm just going to put out a little call for if anybody's got a lozenge, like, for like a Ricola or something. I happen to have gotten a sore throat just for this, Okay, thank you so much. I'm in good shape now. I appreciate it. I sent a distress signal to my wife. She may get it, but this is now good. Thanks a lot. So the topic is global warming, and particularly anthropogenic. And please feel free to come in as you are comfortable. I won't mind. Anthropogenic global warming. Anthropogenic means man-caused. So AGW, anthropogenic global warming, is our topic. The claims of AGW are like this: that during the 20th century, the surge in industrialization has caused a rapid rise in CO2, which is a greenhouse gas. And that as a result of that, the global temperatures have risen to unprecedented levels, and as a result of that, this global warming is going to cause catastrophic effects. Now, this is bolstered by data on CO2 rise in the atmosphere. This data is collected, at the Mauna Loa Observatory. You see it rising. The units are parts per million. And you see we were about 410 parts per million. The little red curve actually wiggles because half the year the plants, there's growth, and plants are taking the CO2, so it's down. CO2 is down in the atmosphere because the plants are sucking it out of the atmosphere, and then it gets released in the winter. So that's what the wiggles are. And this is a greenhouse gas.
Is it half the planet in winter and half in summer? Why?
Well, Mauna Loa is whatever Mauna Loa is measuring.
Gotcha.
I just thought of that on the fly. That was a hard one. Please ask easier questions than that. That was a close one. All right, so greenhouse effect. What is greenhouse effect? We start with something called black body radiation. Think of a horseshoe, and you are heating it in the iron in the fire. At first, it's just black. As you heat it up, it starts getting to be a dull red. If you manage to heat it enough, it'll be white hot. If you were managing to heat it even further, it would be blue hot. And eventually, it would be so blue that you couldn't even see it. It would be, by that point, it would probably come apart, long before that, in fact. But basically, this is called black body radiation. Every object is radiating away as a result of the temperature that it has above absolute zero, minus 270 Celsius. Now, that black body radiation rapidly rises as a function of temperature with a fourth power of the temperature. So that, imagine you had the Earth and the sun, and you turn on the sun. The Earth starts warming. Energy's coming in. And the Earth, as it warms up, starts glowing, at first in radio, and then in the deep infrared, and then in the infrared, and then in the red, and then in the visible. But at some point, it's glowing back. It's with the fourth power of the rising temperature. So eventually, what it's giving out is equal to what's coming in. It stabilizes, and that's the temperature. Without an atmosphere, that would be about zero. I think it's around 0 Fahrenheit. Now you put an atmosphere, primarily water. Water is the most important greenhouse gas by far. And now what happens? This black body radiation that's coming out, mostly in the infrared, happens at some of its wavelengths be just the right wavelengths to be absorbed by a molecule known as H2O. And H2O has various modes of dancing and wiggling, and each one of them has its own wavelength. And at these different wavelengths, it sucks out all the energy as it passes by. As a result of it, it gets very excited. It gets hot. As a result of that, it radiates itself the way that we just said the Earth does. But half of it goes up and half of it goes down. The part that goes down now gets some heat back to the Earth. Now the equilibrium is achieved with a warmer Earth than before. This is the greenhouse effect, basically. There's more here. There is a convective process. It's a little more fancy. Actually, a lot more fancy, but I think this is enough of it for us to get by. So no question that water is a greenhouse gas, CO2 is a greenhouse gas, and that CO2, when the Earth was CO2 starved at the beginning, as you added CO2, and particularly water, the temperature was rising rapidly. But the effect slows down. Now, the evidence for global warming is usually done with a plot like this. This is known as the blue part, which is the temperature, is known as the hockey stick graph. It looks like a hockey stick. This plot appears to show that for 1,000 years, the Earth temperature was stable until industrialization in the 20th century, at which point CO2 rose, and concurrent with that, you can see global temperatures rose, okay? And not only that, if you look at the ice core data, which through the use of proxies and isotopes, you can essentially know the measurement, you can measure temperatures a very long time in the past, hundreds of thousands of years in the past. You look at that, and there is the blue is CO2, the red is temperature, and there they are, very correlated. What's there not to believe? Okay. And not just that, but the climate models all predict a rise in temperature with increasing CO2. So we've got the last 1,000 years temperatures, we've got the paleoclimate, and we've got the climate models all agreeing that CO2 causes a rise in temperatures, a significant rise. And so that is the observations, that is that is what is cited, and as a result, you have a large number of the established institutions of science will have things like this. Earth will continue to be warm and the effects will be profound. Okay, that's NASA. So that is the claim, and I'm now going to examine it a little closer. Okay? So let's look a little closer at the evidence and see what we've got. First, let's talk about the climate models. We just talked about climate models. Let's look at it a little more carefully. The climate models, to model anything that has to do with fluids is extremely hard. So many of you, I'm sure, are engineers, and some of you know about computational fluid dynamics and how difficult that is. The Navier-Stokes equations and all of that. And so it's exceedingly hard. You can only fudge it. You can't really do a good job. You can't closed form solve it. So it's a tough job making a climate model, and the computing resources to do a really good climate model don't exist yet. However, you can parameterize the climate, and then your guesses as to what value of the parameters will let the climate do whatever you want. I'm a physicist, and there's a famous term in physics. With 4 parameters, I can make you an elephant. With 5, I can make it wiggle its trunk. What it means is if you give me a lot of parameters, I can make it do anything you want me to do. I can do a lot with a lot of parameters. You want real truth? Take away my parameters and let me see if I can predict it. That's sort of the idea. These models have a ton of parameters, and look at what's happening. The red trace is the average of the climate models. The green are the measurements. The primary global temperature measurements are from surface measurements, from satellite measurements, and from balloons. Of these, the surface temperatures we're going to examine. There are issues there. But despite those issues, you can see the observations are dramatically, almost the entire population of climate models is out of sync with the measurements. Okay? So the models have problems. The other problem is, if you follow some of these traces, what you see is something even more subtle but very interesting. The climate models have positive feedbacks. A positive feedback is a bad thing. A negative feedback is a good thing. Negative feedback says, whatever bad thing happened, I will undo it. I will do the negative of that and bring it back. Negative feedbacks give you stability. Positive feedbacks give you instability. And nearly all of those models have a lot of wiggle in them. And that a lot of wiggle means they got the feedbacks wrong. I mean, so it's a diagnostic. This is something I learned from John Christie, who's the Alabama meteorologist, and who's at UAH. All right. Now, I showed this hockey stick temperature graph. This is shown in the IPCC's reports. It's been around for about over a decade now. But when the IPCC first did their first assessment, this is what it looked like. The big thing there is the key point here is this thing called the medieval warming period. If that plot is true, you cannot make a case that there is catastrophe waiting. During a time of prosperity on the planet Earth, when cathedrals were going up in Europe, when there were streets named Vineyard out in Scotland, because there were vineyards, when Greenland was green, and there was sheep and there were cultivation there, during that time, temperatures were higher than now. No catastrophe occurred, and there was no excess CO2. There was no industrialization yet, and yet temperatures were larger than now. If this plot is true, it undercuts the claim of anthropogenic CO2 causing global warming. So there is unfortunately a very sad story in the history of science that has to do with the behavior of climate modelers and scientists, not all of them, in the last 2 decades. And there are even email exchanges that through freedom of exchange were found, Freedom of Information Act, where people are talking about getting rid of that hump. And that's how it happened. And it happened, there's a long story, we don't have time for it, but you can ask me afterwards what was done.
How does that disprove anthropogenic warming, though?
Oh.
It can say that it is less dramatic than what
This proves the claim that catastrophic increase, that there will be a runaway effect now, because before it was higher and there was no runaway effect. Why is there a runaway effect now?
Right, but it doesn't disprove anthropogenic warming, though, does it?
Oh, right. And I wouldn't say there is no anthropogenic warming. I would just say the catastrophe is the problem. This is a more recent construction with an average of many data. Again, the medieval warm period is seen. Now, if there is a medieval warm period, another way you can see it is that if as we are warming, glaciers are receding, what should you see? If this is unprecedented warming, what should you see as the glaciers recede? You should see rubble. What if you see instead a forest that used to be there under the glacier? That's what we see. This is the Mendenhall Glacier in Alaska, and that tree is 1,000 years old. That dates back to the medieval warm period. Okay? This is a church from its time back when Greenland was green. It's green now, at least some of the year. People abandoned that in the 1400s because it got so cold, because an ice age occurred, and we are coming out of it. If you're coming out of a cold period, it's going to be a warming. It is not going to be, unsurprising that if you come out of the cold, it will be a warming. Here is that ice core data, the ice core history, temperature versus time, on top of CO2 versus time. And no question, it's correlated. In An Inconvenient Truth, Al Gore says, do these two go together? And everybody says, oh yeah, that goes together. Well, yeah, they go together, but let's look at it a little more carefully. Here's a zoom. Temperature goes up, and on average, 800 years later, CO2 goes up. CO2 is following the temperature, not causing the rise in temperature. Why is that happening? Most likely it's because the solubility of CO2 in the ocean waters is temperature dependent, just like if you take your cold can of Coke and you let it get warm, it'll go flat on you. It's the same effect. But it takes an ocean 800 years to respond enough. But the greatest reservoir of CO2 is the ocean. So as the ocean temperature changes, the solubility changes, the amount of CO2 in the atmosphere changes, and that's what you see. Now, let's go look at the temperature record. Now, we talked about the medieval warm period and the paleoclimate. What about the ground temperature record? I said there were three primary ways of measuring the temperature. They were the satellite data, balloon data, but we haven't had satellites in a long time. But the oldest temperature records in the US go to 1890. And in 1890, we were using a device on the left called the Stevenson screen. That little wooden box had a thermometer and a few other gauges in it, and that's how we measure temperatures. That's how we know temperatures since then from US surface temperatures. Now, Anthony Watts, who made this whole story very clear about 10 years ago, tells a story of when he was in graduate school, and his professor had him go and service one of these Stevenson screens, the one on the left in the picture. And he went and looked at it, wrote some information, and he said there was all this white stuff, went on his hand. And the professor said, yeah, that's whitewash. And it flakes off, and you have to go back and put whitewash back on. And he said, well, why don't you just paint it with latex paint or something? At least you can, it will last a little longer. He said, if you change it to latex paint, the emissivity of paint is different than whitewash. You'll mess up the temperature record because it needs to be whatever they picked then we will need to follow if we want consistency. This is the level of care and detail scientific work needs to have. Now, if that's a problem, how much more is a problem that you now build a concrete wall next to the temperature measurement device, and you let cars park in front of it where the radiator, after the car stops, bellows out heat. And you have all these other features, metal towers. So what has happened is that as time has progressed and cities have grown, a lot of the temperature measurement devices are now more and more urbanized. And what you should do is take this thing, put it farther out in the field, but that's very inconvenient. Who's going to go measure it every day? And besides, I want to just do it electronically. I don't use wires. So the more modern ones, the MMTS device, which you can hardly see in this picture, but it's kind of pointed to, MMTS shelter. It's a little thing. But look at this. There's an asphalt parking lot getting hot as opposed to a grassy field. There is the walls over there. There are air conditioners. And worst of all in this one, the car can park there. And the car, if you put your hand in front of a car after it's been driving, you wouldn't want to, that's not a measure of surface, global temperatures, measure of temperature of the car. Here's another one in Texas, same kinds of problems. There's a radio dish. That thing will get hot in the sun, and it's radiating onto this thermometer. And so you can see what happened. When they brought it to this site, a temperature record just shot up. So this has been a problem that statistically right now, 97% of these temperature sensors are in bad condition in the ways that I've said. All of that orange and all the yellow are, many degrees off. And the red is even worse. And so this is one problem. This is essentially what's called a siting problem. The site is bad. But there's a general other problem. It's kind of related to this. It's called the urban heat island. In other words, if you ask the temperature, what's the temperature in rural Georgia, maybe 50 miles from Atlanta, and then you say, what's the temperature in downtown Atlanta on a summer day, especially a summer night, where everything looks like it's cooling off, but the ground and the concrete and the asphalt are just still glowing and hot. You can feel it. You can touch it. And so they will read bigger, higher numbers. So the surface record is problematic. And this was highlighted over a decade ago. The National Weather Service's solution to this was to homogenize the data, but what it effectively did was made the good data bad too. And this is, by the way, France. This is the heat temperature of various parts around Paris, and Paris is hot and outside is cool. Willie Soon, I stole this slide from him, but if you take the temperature, average temperature reconstruction from rural versus city, the difference is a half a degree Celsius, about a degree Fahrenheit over this period of time, just from the temperature, from the siting problem, half a degree per century. And okay, so these are the things. The medieval warm period is real. It is observable in multiple ways, and it speaks against a catastrophic anthropogenic disaster. The longer-term data, the paleoclimates show an 800-year lag in the temperature record. Something else is changing the temperature and not the CO2. CO2 is responding to it. The surface temperature record is exaggerating the warming because of siting problems and urban heat island effects. And the models that everybody's using for climate policy have tremendous bias in them. They have positive feedbacks, and they don't account for water enough, and the negative feedbacks. And as a result, they all have problems. And particularly the paleoclimate result really exonerates CO2, in my opinion. CO2 is not it. And so then, if not CO2, we ask, well, what is it then? Some warming is occurring. Why is that happening? And what changes the climate? A clue to that comes from an interesting set of data. It is a paper from 2001 by Neff et al. In Nature that shows over a very large number of years, thousands of years, the correlation between cosmic rays and ocean temperatures. Cosmic rays and ocean temperatures. And in fact, if you zoom in, you can see the correlation is quite stark. And what is that? What is that? That's a clue. So the ocean temperature is, it comes from oxygen 18 isotope. Oxygen normally is 16. Its atomic weight is 16. But when the oxygen 18 is another stable isotope that exists. It's a little heavier. So probability of it getting knocked into the atmosphere from the ocean is just a tad low because it's heavy, it needs a bigger kick. And as a result, in warmer years, oxygen 18's relative abundance is a little bit higher. It's always low, but it's higher because there's enough heat to throw it up in the atmosphere. The other one is from carbon-14. Carbon-14 gets created in the upper atmosphere from a process called spallation or sputtering, where protons from the solar wind essentially they hit carbon-12 and make carbon-14. And so those processes essentially produce these two isotopes. One is a proxy for temperature, and the other is a proxy for cosmic rays. Now, what are cosmic rays? We are in the Milky Way galaxy. There's 200, oh, thank you. Yeah, I got one already, thanks. Yeah. But it's good to be safe. So there are 200 billion stars in our galaxy, and when a star is about more than 8 times the mass of the sun, it can go supernova, and it lives a very short time, just a few million years, and goes boom. And when it explodes, that supernova, it makes a shock front that actually accelerates the ejecta, and these particles just permeate the nearby galaxy. These things then, over time, when you're over like a few thousand years, because there are so many of them, and they've been doing this for so long, and they're all in long travel, the apparent flux near us is about this constant. So the cosmic rays are these high energy particles. The lightest weight is the hydrogen nucleus, otherwise known as a proton. The next one is a helium nucleus, otherwise known as an alpha particle, and so on. And it's usually, it's kind of like factors of 10. 90%, like 1 in 10 are helium, and 1 in 10 of that is the next element up. So it's almost all protons. It's all hydrogen nuclei. These protons are very energetic. When they come in, bam, they hit the first molecule in the upper atmosphere, and they make particles, new particles, with quarks in them. Pi mesons, these pi's and gamma rays and stuff. And those things are now got such a big kick. When they hit the next particle, they go exploding into multiple particles. And so you get this thing that's called a shower. In fact, we're all getting showered with these particles as we speak. And these showers, at the bottom end of this cascade is basically the only muons. Muons are a heavy version of the electron, and they don't interact much with anything, and that's why they survive. Now, why is that important? It's important because these guys are related to the climate. If you look at the Earth from space, what you see is, the oceans, the land, and you see clouds. And where you see low clouds, you will see them very fluffy, very white. That's called the amount of whiteness, or the amount of, like if you took a black and white picture, and the amount of lightness of color, that would be essentially proportional to something scientifically called the albedo. It's basically the ratio of the light that comes out from what goes in. So white, like fluffy clouds and snow, have like albedo of 70-80%. And oceans, which look so dark in those satellite pictures, are maybe albedo of 10%. So if the ocean is not covered with white fluffy clouds, it's going to absorb all that energy from the sun. If you've got the fluffy white clouds, a lot of that's going to go back up to space. Clouds basically cause cooling. Now, if you look at the occurrence of low-level clouds, and you compare it to the amount of cosmic rays that are coming in from places on the Earth where cosmic rays are measured, you see this amazing correlation. The two go together very, very closely. And there is a theory as to what is happening. And the theory is basically this, that these cosmic rays, essentially when they're children, they call it in this kind of talk, the children, these daughter particles, and their children, until there's a shower of particles. When they hit aerosols in the atmosphere, they ionize them, and that makes them cloud condensation nuclei. So, and these cloud condensation nuclei become seeds for clouds. So if these galactic cosmic rays make it to the atmosphere, they will make clouds. These cosmic rays that came from those exploding stars eons ago are making clouds now. However, there is a valve, and the valve is the magnetism of the sun. The sun essentially shields the Earth from those cosmic rays, but it shields it at different levels at different times. When the sun's shielding effect is large, which is a magnetic effect, the sun's magnetism is strong, then it shields these cosmic rays from coming. As a result, clouds don't get formed. As a result, temperatures do go up. When the solar activity goes down, the cosmic rays make it right the way through, make the clouds, make it all cold here because the cloud tops reflect the light. So the sun is modulating the Earth's temperature by modulating the amount of cosmic rays that can make cloud condensation nuclei and that make clouds. That's essentially the heart of the matter.
What's the way to measure clouds?
What's that?
How do you measure?
Well, you can
clouds?
with satellites you can certainly measure. Yeah.
Metric the cloud's density
Yeah.
by
Well,
a laser through it or what?
Well, you can just you have cameras. I mean, you can just you can do lidar. You can measure their existences. I mean, if photo is even you can certainly see. If you want to resolve temperature, then you would have to have other methods, and you can use lidar or something.
Doing the blockage of light to do the cloud.
You can just measure a cloud cover just by taking a picture.
Okay.
Yeah, I mean, it's like some of these pictures that I've shown, like that picture I was showing before, that was that's a satellite image, and so you can see them. And here, this is just talking about the difference of albedo between ground and snow and all of that. And so, now a clue. So this is the theory. Now, how do you know this theory is right? Well, there's a few evidences from a long time ago. One of them is very strange. The astronomer Herschel noticed a correlation between the price of wheat and the number of sunspots. The price of wheat in England was correlated with sunspots. How would that work? Well, sunspots are correlated with solar magnetism, which is correlated with the temperature, which is correlated with the price of wheat. And sort of that's how it was happening. But there are events called coronal mass ejections that actually give you even a nicer experiment. Occasionally, the sun will have such a massive storm that the solar wind will have essentially what's a gust, and it would be so strong that it just kind of totally suppresses cosmic rays. Not totally, but really dramatically suppresses cosmic rays on the Earth. When that suppression occurs, suddenly cloud production, drops. And these are called Forbush decreases. And so the previous slide, let me see if I can go back there, just shows the cosmic ray flux from measurements on the ground from one of these events. Whoosh, it goes down by some significant fraction. Within days of that, what we see is multiple satellites measuring various kinds of things. They measure aerosols, they measure clouds. They all see a drop in cloud level after a Forbush event. That the thing happened, and then the clouds went down. And that is a very strong signal that this is what's happening. Yeah. Particles in the atmosphere. It's like a hydrogen, I think, sulfide, that kind of thing. And so the story is like this. The stronger the solar wind, which is the stronger the solar magnetism, there is fewer cosmic rays, and therefore fewer clouds, and therefore more warming. And so there's a book called The Chilling Stars, which sort of goes into this at some detail. So that's the story of, poor CO2 is innocent. It's the cosmic rays. And so we are grateful for CO2. In this meadow that you look in this picture, everything that's green, all of this carbon is from atmospheric CO2. If there's no atmospheric CO2, there is no carbon in any of those plants, and there's no plants. So I wrote an ode to CO2. Though oft maligned and much abused, Carbon must, for life, be used. I thank my wife for fixing it. It wasn't that good at the beginning. So there's the smiley face I found on Google Images, but we put a C on it for the nose and the O's, and that's actually the structure of the CO2 molecule. So there's our friend, Mr. CO2. CO2 is known for something called photosynthesis. We appreciate photosynthesis. Carbon is an amazing element in the periodic table. You know, in the old days, we watched Star Trek or something, and it would say, oh, you know, silicon-based life and, you know, carbon-based life. There is no such thing as silicon-based life. There will never be on any discovery anywhere a silicon-based life. I can say it now with confidence. Why? Silicon is different than carbon. Carbon chemistry is active at the right temperatures where water is actually liquid. And carbon will make macromolecules with metastable bonds, which means it can make very massive proteins and machines, molecular machines, which you can't do with silicon. Carbon is it. Carbon is a gift from God. It really is. And so is CO2. 2/3 of CO2 is oxygen. That's the oxygen we breathe. And we breathe it through this process of photosynthesis, which takes the CO2 and makes the structure of the plant body, makes sugar, which is food for glucose for all animal life, and makes oxygen for us to breathe. What else would you want from a poor little molecule? You know, and by the way, the number one greenhouse gas is called H2O. Let's consider that a pollutant next. How about O2? And what's more is we want more CO2. When I said this at JPL once at our lunch, the guy was so ticked off at me, he just stopped talking. I just like, you are way too crazy for me to talk to you ever again. And he just like snapped. But CO2, we are nearly starved for CO2 in this planet. We're just doing a little better than we used to be. Here is the ambient, this is some professor somewhere, he created this experiment in which on the left, now this is back when CO2 levels in the atmosphere were a little lower. And right now we're at 410, back then it was 385 parts per million. So he made a little tent. He started seedlings and he made a tent with ambient conditions, which was around 385 ppm of CO2. Then he made one with 150 more ppms of CO2, and another one with 300 more of ppms of CO2, and one with 450 parts per million more. That's 830, twice the level of CO2. That's where we might get to in a century if we're lucky. If we're lucky, but we might not be. What's that?
Have to plant a lot of trees.
Yeah, that would be great. It will plant. It will cause the leaf growth. There are two things that CO2 does. Number one, it's essential for photosynthesis. Number two, it changes the shape of leaves and their ability to, it changes their basically propensity to lose water. So that if you have enough CO2, the plant doesn't need as much water to thrive. And so it helps two ways. So you can see that all the way to 800 parts per million, the plant is just happy as a clam. In fact, in greenhouses, people will go all the way to 1,500 parts per million. Okay? And in fact, this NASA website is still up with this, that the greening of the earth is getting greener, crop yields are at record highs. I'm 60 years old. When I was a kid, India was, we heard of starvation in India, right? Children with bellies that were, inflated just because of malnutrition and lack of food. India has been a net exporter of food for decades now. It is just, they are thriving. Their farming is thriving. Of course, there's different reasons for that, but CO2 is part of it. The yields are high. The yields everywhere are higher. If you look historically at CO2 levels, if you look at over large periods of time, we're actually at the nadir. We're at the bottom of CO2. All of this rise in CO2 is like that little blip at the end of that black line. Now, we're at 410 parts per million. At 150, photosynthesis would stop. And if photosynthesis stops, we won't be having this conversation since we won't live long enough to have it. So basically, in a way, if you're going to worry about something, worry about too little CO2. So let's talk about climate alarm and its impact from a humanitarian point of view. Climate alarm is everywhere, of course. You know, any website, just Google it. You can't penetrate the thick layer of appeasism and alarmism that is in the search engines. It's very difficult to actually find information because it's all propaganda for the first 100 items in your search list. Once you can penetrate, you might be able to find something. So you have to kind of do your search a different way. The folks who have really gotten enamored with this say things like this: in the near future, the world may need to resort to lockdowns again. Oh, that was fun. Let's try it again. This time to take a climate emergency. Under a climate-like lockdown, government would limit private vehicle use, ban consumption of red meat, and impose extreme energy-saving measures. This fellow, you don't know him, his name is Schwab. He famously said the pandemic represents a rare but narrow opportunity to reflect, reimagine, reset our world. And now he's saying the next crisis is waiting for us around the corner, and it's the climate crisis. And we're going to do what? We're going to own nothing and be happy. That's the same organization that tells us that. By the way, whose idea is this? No, nothing. It's Marx. This is Marxism. This is just plain, clear Marxism. That's really what it's all about. So this guy, to me, looks like, for this picture, he had to shampoo. I don't know whose shampoo he used, because he doesn't own anything, and he's happy. I don't know whose jacket that is either. Where did he steal that? And of course, these guys go to Davos, which is a beautiful village, in private jets to talk about this, about us not owning anything and being happy. But seriously, this is hypocrisy, but this is not the biggest problem, really. This is the biggest problem. The biggest problem is what's happening to the poor as a result of this. What is happening is that 1/3 of the world currently doesn't have access to enough energy to eat. And so they spend 8 hours a day, typically, to gather dung, to gather wood, whatever they can, just to have heat and to be able to cook. They do this in indoor, basically fireplaces, and the smoke inhalation causes 4 million children a year to die under 5 years old from indoor smoke. Millions of women die from indoor smoke. Indoor smoke is a plague of poverty. James Shikwati, he's a Kenyan economist, he says the African dream is to develop. And that development means electricity, affordable electricity. We have electricity, and maybe we've forgotten what life is like if you don't have it. If there's one thing I would like you to take away from this talk, is the picture of that smoke. It's really that's what it's all about. CO2 is not a pollutant, I claim, but indoor smoke is. Yet the developing world is told to keep inhaling that smoke so we can feel good about reducing CO2 by an imperceptible amount. Patrick Moore was a co-founder of Greenpeace. He left Greenpeace over Greenpeace's drift. And what he said about this is the environmental movement has become the greatest obstacle to development in the developing countries. So this is an oppression of the poor of the first order, to tell them you can't have, you have coal, but don't use it because we don't feel good about you using it.
I am curious about the claim that the environmental measures are what's restricting the development of developing nations. Because I actually read the Paris Climate Accords, and one of the things that you see is that there's massive grants for developing nations to provide energy. So I'm not disagreeing with the idea that we should not I do not think we should restrict carbon-based fuels for developing nations, but I don't think that's what's actually happening politically from everything that I've seen.
Yeah. Okay, so what I've seen is saying no. In fact, it's the other. It's that we will provide you with money if you use electric like panels. But panels produce nothing. They produce absolutely nothing compared to what people need. A panel will serve, will burn, the panel you can afford to give an average African will not barely light a light bulb.
Right, but it's not like they are restricting the development of fossil fuels.
No, they are, because they are working with the governments of those countries to tell them not to develop that, and we'll give you money if you don't have it. So we'll discuss it later. So this is the humanitarian side. This is why it's in a theology on tap talk, because God created us, and we have a duty for protecting human life and protecting human flourishing. Creation was made for us. In the beginning, God created the heavens and the earth, and God saw that all that He has made, and behold, it was very good. God called it good. And God did this. God said this. God blessed them and said to them, "Be fruitful, increase in number, fill the earth, fill the earth, fill the earth, and subdue it. Rule over the fish and of the sea and the birds in the sky, and over every living creature that moves on the ground." And the cultivation of the earth is part of our mandate. It's our creation mandate. Now, I ask you this. If you are a designer of something and you want something to happen, wouldn't you build that into your design? If you're an engineer that, design a wall, would you design it so that somebody leans on it, the whole thing falls? I don't think so, right? Wouldn't it be reasonable to think that God designed the climate system so that the very thing He asked us to do, which is to fill the earth and subdue it, would cause a catastrophic instability and negative and positive feedbacks to blow everything apart? Would that be reasonable to expect? Or would it be reasonable to expect that God would design the climate system to be dominated with negative feedbacks for stability, for ability to absorb whatever is the consequence of us carrying out what He's asked us to do? Self-regulating, self-correcting, that's entirely expected. And by the way, what are we talking about anyway? Are we talking about what are we talking about in terms of these temperature rises? The temperature rises are of the order of the number, in the last 120 years, that's the temperature rise on the left. From 8 a.m. to 10 a.m. of a typical city, and all those different curves are different cities in the country, you get a bigger temperature rise on a typical day. You get orders of magnitude more rise from going from summer to winter than what is expected to happen over a century. Okay, so here's another one. This is temperatures for every year from 1880 to now in Central Park, New York. From summer to winter, look at the variation in temperature. People adapt from spring to summer by putting on a coat, by doing whatever it takes to adapt to a changing climate or changing temperatures from summer to winter. How is it that we're centuries ahead, we would have such a panic over a degree or two? We do that in a typical day. We do that in a typical hour. So there's just something discordant with it all. And the other aspect of this is this, that poverty, and this is Calvin Beisner, who I stole this slide from, poverty is a much greater risk to human flourishing than anything related to climate or weather. He makes this claim, this statement, that you take the 10th percentile income American, the American for whom 90% of the country makes more money a year. That American makes about $40 a day, okay? He can live anywhere on the earth and have enough money for food and shelter to survive and make it. But that's not poverty. When you have poverty at $2 a day, you can't be any place where you can thrive. And so any plan that sacrifices a war on poverty efforts to enable people to rise out of poverty, that sacrifices that for some other climate reason, the climate is not a big problem for humanity, but poverty is. And cost-effective energy is essential for human flourishing. The goal is human flourishing. Does Do the rocks in Mercury care about what is happening in Pluto? Does inanimate universe care about inanimate universe? Why do we care about molecular arrangements anyway? Why do we care what molecules are where in this universe? Why do we care? We care because we care about humans. And if we forget that it is all about human flourishing, we've just sort of like totally lost the idea. It was all about human flourishing. It wasn't about what molecule is where. Conservation of matter says it's going to be somewhere. You know, what do we care? Except that it matters for human flourishing. So human flourishing is the objective. So when we ask about whatever policy, we should ask is does it on the whole affects human flourishing? Alex Epstein does a good job of talking about this. Here is over the last 2,000 years, global CO2 emissions is on the top left. It has gone way up. At the same time, life expectancy has the same curve. At the same time, world GDP per capita has the same curve. And at the same time, world population has the same curve, a similar curve. And this has been made possible through industrialization and fossil fuels. Fossil fuels pack more energy per unit volume. They are safer to transport, and they don't require mines, dug by children, of cobalt and other toxic material. And they actually work. So currently, that little yellow blip at the top is all wind and solar compared to what it takes to power the world that is flourishing. And that green is all the oil and gas. By the way, that bio, I think, includes all that wood smoke that is bad. In terms of, I mentioned climate resilience. I said, Central Park, the temperature changes much more than in a year than we expect in 1,000 years due to climate. At the same time, so we can be resilient against climate. In fact, it's more than that. With energy, you can manage things. You can move things. You can run machinery. You can heat things. You can transport yourself. With energy, you can do this. And you can see that the rise in CO2 is actually correlated with a dramatic drop in deaths, in climate-related deaths. Why is that? It's not because CO2 somehow reduces climate-related deaths. It's just that CO2 is correlated with industrialization and technology and energy production. And that energy production is what gives us resilience against climate-related deaths. And while we're talking about fossil fuels, I'll show you one pretty picture. We have this picture of the fossil fuel industry and all the dirtiness that it has. But it's actually, when it's done right, it doesn't have to be this way. This is a project called Rigs to Reefs. When an oil rig is done, they've essentially figured out what you can do is just either topple it on its side or just cut the top of it. And that structure allows for the growth of sea, barnacles and kelp and all of that stuff. And the fish essentially thrive near these things. And so that's where I'm going to end it. There is more I could say, but I think that's probably a good place to stop. So, all right.